that. Great. Okay, so Quiz Friday. There'll be a homework due on Wednesday morning. Let's see. We've got help available on Monday, Wednesday, 1 to 5 p.m. Let me know if you plan to show up for that. And then help session Thursday at 7:30 p.m. on Google Meet. Okay. Questions on stuff we've got going on in class? I have your exams. I will pass those back at the end of class today. I will, let's see, remind me with 5 minutes to go. I think maybe Dr. Pesh is going to come at the end of class today and tell you about another class. So he may be the good reminder that I need to pass them back. I may pass them back while he's talking to you. All right. So before we left for Thanksgiving break while we had an exam, but 2 days before that, we had actually talked about heat, right? We'd start talking about heat and energy, okay? And chemistry, as all sciences, are going to talk about conversions of one type of energy to another. If you are health professions bound or you're a biology major or whatever, life is really important thing about living things is they convert energy from one type of energy to another. So if we think about photosynthesis, we think about plants are going to accept light energy from the sun and they're going to turn it into chemical energy. Animals will then come along and eat those plants and they'll take that chemical energy and turn it into a different kind of chemical energy. Okay, in each of those processes as we go through, almost no processes are completely 100% efficient. And so, especially in living things, whenever energy gets converted from one form to another, some of it is lost as heat. Heat is also a form of energy. All right, heat energy you never really recover. It goes off, it disperses through the universe. You can't really concentrate it. You can concentrate heat like you heat your house, right? But you're making more distributed energy someplace else to make that happen. That makes sense. All right. Anyway, so we're going to talk about energy. Super important. We're going to talk about it today. And I'm going to assume part of the discussion of we did this like way before break, right? Three lectures before break, or one of them was an exam. I'm going to assume that you don't remember much of it. We're going to review it today, maybe a little faster than we went over it the first time, but we're going to review it today and maybe make a little more progress on it. So we have energy, and we have this thing called internal energy. Actually, let's talk about the system and the surroundings. So you have the system. The system is what you're studying. All right, it might be a reaction in a beaker. It could be a building, right? Everything inside a building. It could be your water bottle. All right, the surroundings. The surroundings is everything else. It's the rest of the universe, in fact. So it's everything that is not the system. Oops, that's going to rattle the whole time. But everything else, the rest of the universe. All right, so this is what we've got going on here. We've got a system we're studying, and then energy can be transferred between the two, depending on what your system looks like, how insulated it is. I mean, there'll always be some amount of energy, but sometimes we can't tell how much it is. I want to also introduce right now the first law of thermodynamics. We didn't talk about this last time. Okay, must be pretty important since it's the first one. Anybody know what it is? Energy cannot be created or destroyed. So what that means is if the system releases heat, all that heat goes into the rest of the universe. Okay? We don't make energy in this process. It's just converted from one form to another, and it's transferred between the system and the surroundings. Okay, if heat is given off by a system, we call that exothermic. Okay, exothermic's a term you're going to see a lot in chemistry. If heat's taken in by a system, so given off by a system, is paper burning? As that paper burns, it gives off heat. Okay? Actually, when ice comes together, when water freezes, it gives off heat when it does that because the water molecules are moving around and then they're not. They lose energy to not be moving around, so they would also give off heat. If heat is absorbed by the system, we call the reaction endothermic. Okay, two important terms you need to know. Okay, and then we had this thing called delta G we talked about. We're going to get back to that, but I don't want to do it just yet. Oops, I want to quick talk about units of energy. And we talked about these last time. We have 1 calorie, or a calorie, which is 1/1000th of a dietary calorie. It's a chemical calorie. It's 1,000 times smaller. 1 calorie is equal to the amount of energy required to raise the temperature of 1 gram of water 1 degree Celsius. Okay? You'd think that would be pretty standard and that would be our metric unit, but that isn't our metric unit. Our metric unit is the joule, and 4.184 joules is equal to 1 calorie. Okay? Joule is the metric unit because this comes from physics. A joule is equal to a Newton times meter. Okay? You don't need to know this, except for when we have to have things cancel out. So there's I can't remember where the place is and what we do, where you need to put your mass in kilograms. I'll let you know when we get to it. Don't know. I didn't see anything we were doing today where it was. But it's a Newton meter, it's physics terms, or a kilogram meter squared per second squared. But it's a unit of energy, and that's your metric unit. Physicists don't care so much about water. Okay. The energy of the system is called the internal energy. So let's say internal energy. It equals all the energy of the system. All right, that includes kinetic, which is energy of motion, and it includes potential energy. And that's like stored energy. Right? Stored energy so energy of motion, pretty easy to think about, right? But that's any motion you would see for molecules. It could be them moving around like this. It could be them rotating in space. Okay, I can't do rotation with my hand. It could be them vibrating. Okay, all that is kinetic energy. Potential energy, if we think about your set of exams here, they have a higher potential energy now than they do now, okay? The potential energy based on gravity. And then stored energy, you know, you have glycogen that's in your liver that's stored energy. Depending on when you ate last, you might be utilizing it now. All right, so what we're concerned with in this class is changes in energy, right? So internal energy is E. It's all that energy. Pretty hard to sum up what all that internal energy is. Okay, there are physical chemists who can do that sort of thing, but really we're concerned with changes in energy. So we could talk about changes of internal energy. So the change in energy, and what this delta means is this means change. All right, the changes in energy is going to be equal to Q, which is heat, it's the amount of heat released, plus work, okay? The work done by that energy. The heat released or gained, we should say. And this is work. And so your book talks about, let's say we've got a piston in an engine. So I don't know if you know how this, some of you probably know how this works for a car. What happens for a car is you squirt gasoline in here, but you squirt it in as a gas. You squirt in, gasoline gets vaporized, it gets squirted in as a gas, and it gets ignited. And there's an explosion essentially in here. It gets squirted in with some oxygen, it gets ignited, and when it gets ignited, the energy from that will push up the piston. You squirt it in, it gets ignited, it's a combustion reaction, it turns into carbon dioxide and water, and it expands and pushes the piston up. So we can think about gas ignites. Let's actually be more specific. Let's just say octane. It's going to form these gases. The gases are going to push the piston up. This pushing of the piston up, this is work. And I guess I could have done the heat as red, but it's going to be hot, and some of that heat is going to leave your engine, so we lose some of that energy as heat. Does that make sense? So the system, if we thought the system would be the octane plus, so we think about octane looks like this, C8H18 plus oxygen. Okay, we have some amount of octane and oxygen that gets added in there. That's our system. That system has an internal energy. When it turns into carbon dioxide and water, it's still our system. It's not balanced, and I'm not going to bother balancing it. Okay? When it turns into carbon dioxide and water, this is still our system, but it's going to lose energy. Okay? We have potential energy stored here, and combining the oxygen with helps release it. And then this right here, we're going to get that energy is released, and some of it turns into work, and some of it turns into heat. Okay? Does that make sense? Sort of abstract. If this happened, your book has this example as well. If we had this happen and we didn't let the piston move, no work could be done, okay, because no motion is happening, and all of it would be lost as heat. Questions? Okay. So when we talk about work here, we are going to mostly focus on pressure volume work. We're not going to do a practice problem for this, but the work of the system is going to be equal to minus, okay, it's a convention based on if the system does work, it is losing energy, right? We look at our equation up here. Negatives are when heat's given off, when work's done to something else. So if the system does work, it pushes that piston, that ends up being, we call it negative work. It's pushing on the piston, and that's going to cause our energy to decrease. energy is leaving the system. If it gets hot and heat comes off, our heat number is going to be negative. Heat is leaving the system, energy is leaving the system. Does that make sense? You're going to see this negative positive convention throughout chemistry. So it's equal to negative times the pressure times a change in volume. Okay? There's more with this derivation. I think I was looking at it in the book, and I was thinking back to when I was in college, and I remember going through all this stuff. It's a derivation of I'm going to give you an answer. I'm going to skip the derivation. Okay? If you end up in physical chemistry, you can go over this again, and then it'll make more sense at that time. I haven't used the derivation for this very much, but essentially, your book goes and it defines work of the system like this, and then it goes and it's going to talk about more about pressure, volume work, and things like that, and enthalpy. But remember, we want to get to enthalpy. So enthalpy is the heat released or gained, okay? Enthalpy is the heat. Enthalpy is heat. Let's just do it as just heat. It's not released or gained until we make it a change. Enthalpy is heat at constant pressure. Or actually, let me take the constant pressure out. We're not at the constant, so the change is going to be that. Enthalpy is heat. Okay, and what we're going to do for a symbol for that is we're going to use H for that. And so this, I'm going to check with my colleagues and see how much they want it emphasized. I'm not going to put it on your homework for today, probably. I might. It'll be easy problems if it is, probably, because it's a pretty easy equation. But change in heat is equal to, or change in enthalpy is equal to heat at constant pressure. So this derivation here and other stuff is important for this. But that's what you need to know. Generally, when we do reactions in the lab, we take a beaker of something and a beaker of something else, and we combine them and a reaction occurs, right? That's in air pressure. It's at constant pressure around us. Okay, so that's why this is important. But all we need to know is our change in enthalpy in pretty much anything you guys are going to do is going to be equal to heat. And so, once again, we can talk about change in heat of the system, and when that change of heat is negative, that's exothermic. And when that change of heat is positive, that's endothermic. Okay, this is heat given off by the system. And this is heat absorbed by the system. Questions so far? So it's mostly a review of, I've added a couple terms, but it's mostly a review of stuff we talked about before break. All right, now I want to remind you of some of the equations we had. So we can talk about heat and how it relates to temperature. All right, so how temperatures change with the amount of heat given or absorbed. Temperature is the kind of an average, it's an average or indicator of the average motion of molecules. Okay, and we talk about temperature. We're going to talk about specific heat. right, so specific heat is going to be the amount of energy required to raise the temperature of an amount of substance by a quantity of substance by 1 degree Celsius. I'm going to say 1 gram of substance by 1 degree Celsius. Or Kelvin, they're the same. The degree size is the same. Okay, but then I'm going to put a little, the units can change. So in other words, it doesn't have to be a gram, it could be a kilogram, it could be a pound, it could be anything. It doesn't have to be a degree Celsius, it could be a degree Fahrenheit, it could be, well, we really only do Celsius, Fahrenheit. I don't know of a fourth temperature scale. I'm sure one exists. All right, and so then we have an equation for that. So specific heat, which your book uses an S. I was always taught a little c, but I'm going to follow your book here. But you might see a little c someplace else. Is equal to the amount of heat required to raise a gram by 1 degree Celsius. Okay? And another rearrangement of this, I could multiply both sides here by m times delta T. And if I rearrange that, I can get a useful equation. This is useful as well. Actually, let me rewrite that slightly. Let me rewrite it so it looks more like the algebra. Okay? So that's a useful equation for us to do. Let me look at this problem down here and just see if we're ready for it yet. Looks like we are. All right, so let's go ahead and use this equation to solve something. Let me label these. This is specific heat. This is mass. This is heat. This is change in temperature. Yeah, all right, go ahead and do it. Go ahead and try that one. I'm going to give you, let's go ahead with 3 minutes for that. Call me over if you're not sure what to do or where to get started. Anybody want more time? Okay. So this is essentially a plug and chug, right? We're solving for specific heat, right? So for solving for specific heat, we're going to use this equation. What's our heat in this instance? What do I put on top? Yep. 1217 joules. Okay. What goes down? What's our mass? 230 grams. 0.0 to keep our sig figs. What's our change in temperature? 5.88. And we don't have to, because a degree Kelvin and a degree Celsius are the same degree size, and we're looking at a change in temperature here, we do not need to convert to Kelvin, okay? It's only when we're comparing absolute Kelvin values. What did somebody, rather than me get my calculator out, somebody want to give me what they got? Looks like it's going to be three significant figures based on the temperature change. Anybody do it? I stop you all too early? Yeah. 0.9. Okay, that doesn't sound wrong. It's a metal. Okay. The only way it sounds wrong is it seems too big to me. So 0.9. Anybody else get 0.9?
I got 0.899. So
899. Okay. So 900 if we're going to go for significant figures. And what are my units? Oh, actually, it's not so bad because it's not calories, and the ones in my head are calories. Joules, right? I'm just going to carry my units over. Joules are on the top, grams are on the bottom, degrees Celsius on the bottom. So it's 0.900 joules per gram degree Kelvin. Okay? All right, so we've got that. So let's see if we can figure out what metal that is. I actually have a table down here. Let's see if it fits. Let's see if my table has stuff in joules. Oh, it's in calories. So we need to put this into calories. That's a good practice, right? What is this in calories? All right, if you remember, there's 4.184 joules per calorie, right? So I have 0. This is good old dimensional analysis again. Joules per gram degree Celsius. Okay, and I know that if I have 4.184 joules, I have 1 calorie. Joules cancels with joules. I'm going to end up with calories. And what do I get from that? 0.9 divided by 4.184. 2-ish. Or 0.2-ish. All right, I've got 2.15 or 0.215 calories per gram degree Celsius. Now let's look at our table. Is it one of our metals? What metal do we think it is? Aluminum. Yeah, aluminum's good. We don't actually, it's interesting. We don't have, so aluminum's conductive. I'm trying to think if the heat capacities go with this or not. Aluminum's very conductive. Gold's very conductive. Copper's very conductive. Okay? These are all great for cooking because they move your heat really well. I don't know whether they also have high, this is a high specific heat capacity for metal. Anybody know why you don't cook with copper directly, why you always have those copper, if you have a copper, they have copper pots and pans, right, but they line them. Anybody know why you don't just directly cook copper? Tastes bad. You make copper reacts with the food and it tastes really bad. So you want to, you like copper pans because they conduct heat really well. But you don't want to cook directly on the copper because it's going to make the food taste bad. Okay, I see what our next problem is. which may or may not be related. I'm not sure if it's related to what you're going to be doing in lab. I was talking with Dr. Livingston. I should actually just read your lab manual, but I have not done that. So we have this thing called specific heat capacity. Okay, we can also talk about heat capacity, which is different. Heat capacity is the amount of heat required to raise the temperature of an object, not a gram of substance, by 1 degree Celsius. So what we're getting into here, I don't think I declared it as calorimetry yet. Now we're getting into what's called calorimetry. I'm just going to put it up here, which is essentially, it's the science of measuring heat changes. Okay, so the heat capacity, so that changes our equation. Before we had specific heat capacity, right? And so specific heat capacity was our heat divided by our mass times our change in temperature. But now our mass is part of the object, right? The whole object is all the different things in it, and they have a mass all together. So what's going to happen is we're going to have our heat capacity, which is a capital C, is going to be equal to just our heat over our change in temperature. Okay, so this is for an object. And so, like I said, you might have a calorimeter. You're going to have these calorimeters you work with, but you could take your calorimeter and you could calibrate it. You could figure out what its heat capacity is. You could take a thing you're going to be measuring heat in, and you could, you've got your calorimeter. If it's made of metal, you've got the walls of it that are made of metal, the water in it that heats up. You've got all sorts of things that all together you need to raise the temperature of. And so you might calibrate it by running a reaction at where you knew how much heat it made and see how much the temperature went up. So here we've got a boiler system requires 15,000 joules to heat it from 25 degrees Celsius to 200 degrees Celsius. Wow, okay, so it's under pressure because you can't actually go above 100 degrees Celsius for water unless you're under pressure. Okay, at 100 degrees it would all boil off. But that's fine. A boiler system. What is the heat capacity for this system in kilojoules per degree Celsius? Okay, well, it's going to be a pretty easy problem. 2 minutes. Okay, go ahead and try that for 2 minutes. You're calculating the heat capacity. You're given the heat. You're given the change in temperature. All right, anybody need more time? Nod. Okay. So what we've got here then is we're given our heat, and it's even in the right units. We don't need to change them, right? Because it wants kilojoules. We're given our change in temperature we're not given, right? Okay. So our change in temperature is going to be equal to what? We're going to go with temperature final minus temperature initial. Okay. All right. And so 200 degrees Celsius plus not plus, minus 25 degrees Celsius or 175 degrees Celsius. All right, and so then we're going to go 15. We have our temperature right there, right? We have our heat. So we're going to put our temperature, or I'm sorry, our heat over our temperature. So 15,000 kilojoules to raise the temperature 175 degrees Celsius, and that's going to be equal to our heat capacity. And did anybody get that? A little louder? 70, what? 85. 85.7. So I'm going to go with 86 for significant figures. 86, what are our units? Kilojoules per degree Celsius. Okay, questions? That's heat capacity. And what's going on with this boiler is the boiler is made of metal, right? This might be a boiler on an old house. It might be a boiler in Texas, actually. We have radiated heat, radiator steam sort of heat as well. But you've got in that temperature change, you've got all sorts of stuff going on. The water going from the heat capacity is actually going to change for this depending on the temperature, because the water heating up, it takes a certain amount of heat to heat it up, then it takes a certain amount of heat to turn it into steam. Okay, that's going to be most of the heat. And then once it's steamed, then you're heating it up some more, and that takes different. The specific heat capacities of that water are going to change over that process. But really, probably most of the heat there is turning liquid water to steam, not heating it, not changing the temperature. All right, questions? All right, so then we had talked about, we worked a problem, and this is going to be similar to what you do in lab, is what if you combine two materials? Two materials in an isolated system. Or let's say insulated system. Okay, the heat can't escape, right? Because you're in an insulated system. So what that means is that, let's say the typical things we do is we drop like a block of metal into some water. Maybe I should do my hot metal in red, but we can talk about if that's hot metal, we're going to have heat is going to move from our metal to the water until the metal and the water are the same temperature. Heat will leave the hotter object, the hotter material, let's say, until both are the same temperature. And then you won't have any heat transferring from one to the other. All right, so that's what's going to happen here. And so what that means is if I can have the heat of material 1, okay, that's going to have a change in heat. We can talk about the heat transferred from material 1, and that's going to be equal to the heat gained by material 2, or lost. Okay, I've got a negative sign here. One of these is releasing heat, the other one's absorbing heat. Okay, so one will have a negative sign and one will have a positive sign, and by putting that negative sign there, then they're equal. Otherwise, we'd have a difference in sign there. in the answer. Does that make sense? Okay, but you remember from up above and from a couple weeks ago that heat is equal to the specific heat capacity times the mass times the change in temperature, right? So we can substitute this in for that, and we can say that I'm going to substitute in for both sides here. And so we can say that the specific heat of material 1, I'm just going to write a 1, the specific heat of 1 times the mass of 1 times the change in temperature of 1 is going to be equal to negative the specific heat of 2 times the mass of 2 times the change in temperature of 2. Okay, you guys remember that from maybe 2 weeks ago? Maybe vaguely? Through a turkey haze? Okay. You guys were all thinking about chemistry over break, right? Okay, so so this gives us a way. What we can do is if I know, this is one of those equations, I've got 6 things here, right? You may have noticed this. If we have one equation, we can only solve for one unknown. So what I've got is you'll have problems where you can either, you're given 5 of these things or you can solve for 5 of those things. And then you put the 5 in and you solve for the 6th. So here is here's a problem. Oh, it's long. All right, so here's a problem that we can work here. Go ahead and start in on that. This may be where all we get to. I guess that's okay. Maybe. I'm going to give you, I guess, 3 minutes, which probably isn't enough time, but try and work as far as you can through this, and then we'll work it real quick because I'm not sure if Dr. Pesh is showing up today, and I'm not sure when he's showing up today. If he is. Open the door a little more. And call me over if you're not sure where to go, where to start.
So what you do is you're given that Keller mercury experiment on metal, the mass of the sample, so the sample equal to 2 grams. Let's call that mass. So mass 1 is going to be 2 grams. We've got our water is 95.4 grams, right?
Let me help you out with one thing here. So we'll do this in calorie. Remember that the specific heat of water, a calorie is defined as the amount of energy required to raise 1 gram of water 1 degree Celsius. So the specific heat of water is 1, okay, by definition.
So you just see the water is that. That's going to be S2. This S1 is your sample. How much water do you need? Right, so that's S2. S2 grams. And what's the temperature for the yeah, nice job. So then see if you can do the change in temperature of the substance. And I think the things, 4 things, the mass, and the change in temperature of the mass. No specific heat of water. Anybody else have questions?
So you're needing to solve for your change in temperatures here. You're given a starting temperature and an ending temperature. one more minute.
Right. Good question here. We'll talk about it. But what's the temperature? What's the final temperature for the metal? Anybody tell me? Yeah. Anybody got it? It's this. Remember, they have to come to thermal equilibrium. So they exchange heat until they end up being the same temperature. So the final temperature of the water is the final temperature of the metal.
Okay, let's go ahead and look at this then. So we've got how much heat is absorbed by the water. Well, we know that our heat is equal to our specific heat capacity times our mass times our change in temperature, right? Our specific heat capacity for water is 1, and this is the infinite significant figures because it's a definition, 1 calorie per gram degree Celsius times the mass of the water. What is it? 95.4 grams of water times the change in temperature, and this is going to be 1.3 degrees, right? If I subtract those two, I'm just going to do it for speed here in my head. But I subtract those two numbers. Actually, I won't do it for speed. Let's do 23.2 minus 21.9 equals 1.3 degrees Celsius. Okay, that's our change times 1.3 degrees Celsius. Put that into my calculator. Anybody done that? 95.4 times 1.3. All right, so that's a big number. Well, that makes sense. 124 is what I've got, or so that's going to be equal to 120 if I round for significant figures. No, it's not joules, we're calories, right? The way I know I'm calories is because Celsius cancels Celsius, grams cancels with grams, and I get calories left over. All right, that's how much heat was absorbed by the water. It was absorbed, so it's positive. How much heat was released by the metal? Do you remember that your heat of, so in this case it would be water, is going to be equal to negative of the heat transfer of the metal, right? So this one's easy. It's just going to be 120 calories. And it says released, so I don't need to put the negative sign in front. All right, I'll probably, if you say released or you say absorbed, you've got that part correct. I'll probably just ignore the signs. What's the specific heat of the metal? So now I can use this equation again. I could have done C just with one equation. I could have done it with this whole equation together, okay? But this is breaking it down. So the heat of the metal is the specific heat of the metal. Whoops, that's not right. Let's use our rearranged equation that we had up above. Our rearranged equation that we had up above was heat over mass times change in temperature. We turn that into change in temperature. All right, and so I've got 120 calories divided by the mass of the metal. What was the mass? 52.4 grams. 52.4 grams of metal times the change in temperature for the metal that we said was, oh, we didn't say. That's going to be, it starts at 100 degrees, was that right? Okay, so 100 degrees Celsius minus 23.2 degrees Celsius is the final temperature because it comes to thermal equilibrium. If I subtract those two, I get 76.8, okay? And so I can go ahead and put that all in my calculator. I could have done it if I knew how to use parentheses on my calculator. I've got 0.029. That seems too low. Is that what other people got? Okay. But maybe there's a metal that matches that. Oh, 0. No, it's still too low. But anyway, 0.02. What have we got? Two significant figures here. 0.030. And that's going to be calories per gram degree Celsius. I just want to, okay, well, let's come down and take a look at it. Okay, well, there is one that, okay, I didn't know that. Which one do we think it is?
Lead.
Lead, right, there we go. Okay, I clearly don't know my specific heat capacities of metals very well. All right, so that matches pretty well. So we're going to call that lead. Questions? All right, I'm going to take a peek out here, and if not, I'm going to do one more thing. Nope. All right. So I want to talk about heat of solution. So heat of solution. All right, is how much heat is absorbed when something dissolves. How much heat is absorbed or released when something dissolves? Okay, in water usually. Most of our examples are going to be water. If you're, like I said, if you're biology focused at all, it's going to always be in water. And so it's still the same thing. We're going to have our heat of solution is going to be equal to the specific heat of that thing, okay, times, in other words, how much heat's evolved. It's going to be, actually, it's negative here because we're talking about the solution, but the heat of solution is equal to, and that's going to be equal to the enthalpy of solution. Just remember this enthalpy term, right? It's a change in enthalpy. That's that heat are the same thing. Times the mass of whatever that solution is, times the change in temperature. But essentially you've got how much stuff you dropped in. So let's go ahead and take a look at this one. And so we talk about heats of solution. Often things will become hot, sometimes they'll be cold. If I take hydrochloric acid and I dump it into water, the water will get hot. It dissolves in, the hydrochloric acid dissolves in the water and it gets hot. It gives off heat when that happens. Okay? I talked about those chemical cold packs before, right? When you take those chemical cold packs, you're breaking that cold pack, and I think certainly this happens for ammonium nitrate, okay? Ammonium nitrate gets released into water. When it releases, it goes into dissolves in water, it absorbs heat, and so the cold pack gets cold. All right, so we have a couple minutes left here. So we have constant pressure, calorimetry experiments. So that's important for our envelope being, you have 20 grams of solid being added to 100 grams of water. As the solid dissolves, the temperature of solution raises by that much. What's the enthalpy of solution in kilojoules per mole? Okay, so you're going to get out a mass, and then you're going to have to turn it into moles. Maybe just since we're short on time, let's change things to moles, but let's just try for the mass. Right? And while you're working on that, I'm going to hand your exams back. Why don't you keep them upside down so we can get as far as possible on this problem.
We're not doing it this week. Assessment.
All right, is anybody done?
In Spanish. We're still doing it.
I'm not going to have time to work with it. Does anybody
Go back to
want
classic, I guess, right?
to share their answer? Tyler.
Just for multiplying everything I got, but if it's math better.
1,500. And what's the answer? This is going to be
Joules
per gram, joules per gram. Did you get that, Jack? Okay, so 1,500 joules per gram. I'm going to just write the answer down there, but I got to do my notes. But if you didn't get that, you want to ask about it, let me know. I'm going to continue to hand these back. You're welcome to look at yours now. You're welcome to take off for the next class. The answer key for this is posted. Maybe we'll talk to people about them as well. I'd encourage you to look at the answer key first and then come talk to me, but if you want to just talk to me, that's fine too. Yes.
Can I be with you at 1:34?
Yes. See you then. Was it 1,500?